Okay, let's dive right into this explainer. If you've ever felt like math is just a rigid set of unbreakable rules, well, prepare to have your mind expanded. Today, we are exploring a chapter that literally adds a completely new dimension to our reality: complex numbers and quadratic equations. You know, the legendary mathematician Carl Friedrich Gauss once said that mathematics is a royal realm of pure logic. But historically, even this queen of sciences had some completely unsolvable mysteries. For centuries, mathematicians would encounter very specific equations that just seemed broken. They'd hit a massive wall, throw their hands up, and literally declare the problem impossible.
So here is the exact mystery I'm talking about. How on earth do you solve x squared plus 1 equals 0? I mean, if you just move the 1 over, you get x squared equals -1. But we've all been taught since day one of basic algebra that squaring any real number, whether it's positive or negative, always gives you a positive or at least non-negative result. 2 squared is 4, -2 squared is also 4. So what happens when a fundamental equation demands that a square results in a negative number?
Well, to figure that out, here's our roadmap for building this new mathematical universe from the ground up. We'll start with the impossible problem, meet the imaginary unit, look at the anatomy of complex numbers, cover the rules of algebra, learn about modulus and conjugate, and finally, map the Argan plane. Let's get to it.
Starting with Section 1, the impossible problem, hitting a mathematical wall.
If you recall the quadratic formula, you know that the second the part under the square root goes negative, you're totally stuck. In our everyday system of real numbers, x squared equals -1 just doesn't have a solution. The entire real number line, stretching infinitely in both directions, doesn't contain a single valid value for this. But to cross this roadblock, mathematicians didn't just give up. Instead, they creatively invented a completely new tool to bypass it entirely.
Which brings us to Section 2, meet the imaginary unit, the key to the universe.
Enter the hero of our story, I. By literally just defining the symbol I as the square root of -1, we instantly bust open a massive doorway to new possibilities. I know, it sounds a bit like cheating, right? Just making up a letter. But by actively declaring that I squared equals -1, we suddenly have a valid working solution to x squared plus 1 equals 0. That one elegant little definition is the seed from which an entire branch of mathematics grows.
All right, Section 3, Anatomy of Complex Numbers, building a new form.
So let's mix our new hero I with the everyday real numbers we already know and love. A complex number, which we usually just call z, takes the form a plus ib. It's basically a hybrid. The a on the left is the real part, just a standard normal number. The b on the right is the imaginary part, because it's securely attached to our new friend I. So for example, in the complex number 2 plus 5i, 2 is your real part, 5 is your imaginary part. It's a perfect partnership.
Now check out this fantastic rhythm when we multiply I by itself. The powers loop in this beautifully predictable repeating cycle. I to the first is just I. I squared, by definition, is -1. Multiply by I again, and I cubed becomes -I. Multiply one more time, and I to the fourth brings us right back to +1. It's this perfect four-step dance. I, -1, -I, 1. And it just repeats forever. But hey, quick heads up here. We've got to be super careful with our old assumptions to avoid a classic trap. You probably remember the rule that the square root of a times the square root of b is the square root of a times b, right? Well, actually, scratch that. That rule totally breaks down if both numbers are negative. If you blindly multiply the square root of -1 by the square root of -1 using the old rule, you'd get the square root of +1, which is just 1. But we know that's absolutely false. I times I is I squared, which is -1. It's a subtle but really vital distinction in this new universe.
Moving right along to Section 4, Rules of Algebra, Order in the New Universe. You might be worrying that introducing this strange new number just breaks math, but the universe doesn't descend into total chaos. The algebra of complex numbers perfectly obeys all those familiar rules you already know. The commutative law, the associative law, the distributive law, they all hold completely true. You can add, subtract, and multiply these numbers using the exact same logic you learned in basic algebra. You just group the real parts together, group the imaginary parts together, and keep everything perfectly organized.
Now, division is the one operation that looks a little tricky at first glance. But honestly, if you just follow a few logical steps, you can gracefully untangle it. If we want to find the inverse of 2 minus 3i, we just put it under 1 to make a fraction. Then, we use a really clever trick, multiply both the top and bottom by 2 plus 3i. When we simplify the bottom, the imaginary terms just cancel out, that I squared becomes a negative 1, and boom, we're left with a nice, clean, real denominator of 13. So we get our final answer neatly split into real and imaginary parts. 2 over 13 plus I times 3 over 13.
Okay, Section 5, Modulus and Conjugate, Essential Tools.
So, the first essential tool in our belt is the modulus, denoted by those absolute value bars you see around the z. For z equals a plus ib, the modulus is simply the square root of a squared plus b squared. If you're sitting there thinking this looks an awful lot like the Pythagorean theorem, hit the nail on the head. The modulus acts exactly like measuring a distance. It takes the real and imaginary parts and gives us a concrete non-negative magnitude, basically a measure of how big the complex number is overall.
Tool number 2 is the conjugate, and this one's super straightforward. If you have a complex number z equals a plus ib, its conjugate is literally just a minus ib. You simply flip the sign of the imaginary part. As we saw in our division example a second ago, the conjugate is absolutely your best friend for simplifying messy equations. When you multiply a complex number by its conjugate, all the imaginary parts vanish completely and you're left with a pure, real number.
Finally, Section 6, Mapping the Argan plane, Visualizing the invisible.
This is where we get the grand finale, transforming all that abstract algebra into actual, beautiful geometry. And this is a massive conceptual leap. Up until now, our traditional view of real numbers meant mapping them to points on a single, flat, one-dimensional line. But now, because a complex number has two independent parts, a real part and an imaginary part, it simply cannot fit on a single line anymore. Instead, we are literally expanding math from a flat line into an expansive two-dimensional grid called the Argan plane. The x-axis handles the real part, and the y-axis handles the imaginary part.
In this incredibly elegant system, complex numbers can be represented purely as coordinate points, or ordered pairs. So 2 plus 4i, that simply becomes the point 2, 4 on our graph. Negative 2 plus 3i is plotted precisely at negative 2, 3. This geometric view is so powerful that, back in the 19th century, the mathematician W.R. Hamilton defined complex numbers purely as these ordered pairs, specifically to avoid using that spooky term imaginary numbers. He proved they aren't imaginary at all, they're just points in a two-dimensional space.
So as we wrap up this explainer on the chapter of complex numbers, I want to leave you with this final thought. We started with a problem that seemed entirely impossible, but by simply imagining a solution, we unlocked an entirely new 2D landscape of mathematics that behaves with perfect logical consistency. If these numbers perfectly map out a two-dimensional plane and allow us to solve very real, highly complex equations in fields like physics and engineering, is imaginary really just a historical bad name? I'll let you be the judge of that. Thanks so much for joining me on this mathematical journey.